AQA, A-level physics, and this is for the electronics option, and this video is about communication systems. So now this block diagram, it's on the specification and you should basically learn it. It's a real-time communication system. Real-time as in you're not storing any information. This is two people or places communicating with each other as it happens in real time. And what you need to be able to do is to recognize all the different blocks in it and be able to talk a bit about what each one does. So you should learn that diagram. You should be able to describe what each component does, which is what I'm going to do now. So the input transducer, for example, a microphone, or it might be a camera or a computer, and it converts the data into an electrical signal. The modulator, now to modulate means to change, okay, to kind of do stuff to it. It modifies the electrical signal to match the transmission path. It may be an A to D converter, analog to digital converter. If it's AM or FM, then there's, which we're going to talk about in another video, there's various stuff that you need to do to the signal. I'll talk a bit more about modulation in a bit. Amplifier, boost the signal to an appropriate level for transmission. And then some kind of a transmitter, which may be some kind of an antenna, or if it's an optical fiber, a laser diode or an infrared LED, converts the signal into the appropriate form for the transmission path. The transmission path, the ones we need to worry about: radio waves traveling through free space, or microwaves, electromagnetic waves traveling through space, through the air. Light pulses traveling through optical fibers, electrical signals traveling through cables, for example, coaxial cables. Okay, the rest of this diagram, the receiver, for example, an aerial or a photodiode, receives the signal, converts it back into an electrical signal. Amplifier, the signal, you might filter it for noise to get rid of noise, and then the signal you receive might be very weak, so you need to boost it a bit to make the amplitude bigger, so that the rest of the system can do things with it. So an amplifier. A demodulator, so if it was an analog to digital converter, then you need a digital to analog converter at the other side. If it's AM or FM modulated, then you need to change it back into the audio signal that it was to begin with. So a demodulator. And then some kind of an output transducer, which may be, for example, a loudspeaker, turning your electrical signal into sound. Okay, you may need to amplify it first. Now there's a couple of things which I couldn't really slot in anywhere else in any other video, so I'm bunging them here. Two types of modulation which apply to digital signals, which you need to know: pulse code modulation and time division multiplexing. These apply to digital signals. So what are they? And basically pulse code modulation is if you do your sampling. Do you remember you sample? For example, on this diagram here, it's 3-bit samples, but it might be 8-bit or 16-bit or 24-bit. Well, basically, you look at the voltage and you take a sample, and you've got your 8 bits, for example, but that's parallel. So you need to change it to a serial signal. So it's basically going from a parallel 8-bit parallel signal, yeah, for each sample, to a serial, a string of bits, and then you transmit this serial stream of bits. And it's all controlled by a clock pulse to make sure that everything happens. You know, when you take your voltage, nothing happens until that particular sample has been dealt with. Sample and hold, it's called. Anyway, that's all pulse code modulation is. Time division multiplexing, you can actually, through a single optical fiber, you can have hundreds of different telephone calls or data streams going through a single fiber. Okay, how is that possible? Time division multiplexing. Well, what's that then? Well, basically each data stream, which is lots of ones and zeros in a line, each data stream is split up into packets, and then you basically take turns. Here I've only got 2, but as I said, it could be 100 different data streams. And if you have enough bandwidth, if you have enough room to actually sending it, if you're sending enough bits per second, then you can actually send loads and loads of data streams if they take turns sending packets. Okay, within each packet, just as on the internet, each packet will contain some additional data identifying things like what stream it belongs to and stuff to get it synchronized with the other data streams, etc. So this is time division multiplexing. It's basically taking turns, send a packet from that stream, then a packet from that stream, then a packet from that stream. Transmission media, the ones that we need to worry about is metal wires, optical fibers, and electromagnetic waves, basically radio or microwaves. Okay, you should give some details about how they work. You should be able to discuss advantages and disadvantages. We'll see at the very end of this video the kind of questions you might get, and a lot of it is to kind of talk about comparing them in terms of security, ease of use, how expensive they are, and bandwidth. Bandwidth means basically how much information that they can send in this context. So metal wires. Metal wires, you've got the transmitter and the receiver are joined together by a copper wire. For example, there's the aerial on the roof and there's your television, and they're joined together by a copper wire. Okay, you've got coaxial cables. Looking at this, coaxial, so they've got the same axis. Yes, radio and television. High frequency signals up to about a gigahertz, suitable for. You've got some shielding. This copper on the outside shields it from noise, and it's pretty good at shielding from noise. Not very secure. If you're carrying sensitive information, like, if it's like your bank details going down the internet, then it is hackable in terms of picking up the signal and naughty people doing things with it. But anyway, that's a coaxial cable. Twisted pair cables used for computer networks. In fact, the Ethernet cables, the cable going into the back of your computer carrying the internet will be one of these. Twisted pair cables, up to about 250 megahertz. Several pairs of wires twisted together, and that gives you some noise immunity. They are cheaper than coaxial cables, and relatively secure. And then lastly, just plain copper wire. This is the cheapest. It's just a couple of thin copper wires, more prone to noise. This kind of thing, if you've got headphones on at the moment, going from the headphones to your computer is probably just plain copper wire. Higher frequencies might be lost, but it's okay for audio signals, as I said, for headphones. Not very secure, but you wouldn't use it for very long distances anyway. So those are 3 solutions using metal wires, and there's advantages and disadvantages for each of them. Optical fibers. Now, you've done loads about optical fibers on the core syllabus, and I'm not going to repeat that here, but basically very large bandwidth. As I said, it's possible to send 100 different telephone calls down one single fiber. Very thin glass fiber. There's what we call the mono mode, which is 8 micrometers, or the multi-mode, which is 100 micrometers, talk a bit more about those in a bit, but 8 micrometers, think about how thin that is. I mean, 100 micrometers, that's 1/10 of a millimeter. Yeah, very thin fibers. They are immune to noise, so any kind of electromagnetic interference doesn't affect it in the slightest. Very secure, okay? Disadvantage is that you do still need a physical link between the transmitter and the receiver. This is if you're comparing it with, let's say, radio or microwaves. You still need a physical link. You need to join together the receiver and the transmitter. Lots and lots of fibers could be in a cable, and then obviously that cable can supply data to many different places. These are the types of fiber I mentioned before. A multi-mode fiber is thicker, okay? There's some attenuation of the signal, but which a lot less. Attenuation means it gets weaker, but less than for a copper wire. Modal dispersion, do you remember what that is? If you don't, look it up. I'm not going to talk about it. Yeah. And how do you avoid modal dispersion? Well, you have a very thin wire, and so that's the mono mode wire, yes, or single mode fiber. 8 micrometers, very thin. There's less attenuation than the multimode fiber, less modal dispersion because it's thinner, and it's smaller, so it takes up less room. Disadvantage, it's harder to make, so it's more expensive. Now look at this, electromagnetic waves. What on earth is this chart? This is the UK frequency allocations. Basically, if I set up a radio station in my backyard and I decided to, send out radio waves to all of Middlesbrough where I live, I might get in trouble with the police, because basically all of the frequency, all of this band, all electromagnetic waves, all the different frequencies are, they're all assigned to different things. Some of them are assigned to radio transmission and TV and satellites, some for maritime, some for the police, some for the army, some for amateur radio, some for aeronautics and air traffic control. It's all divvied up and it's all accounted for, and people have to pay an awful lot of money for a license to transmit. Okay, you might have heard of something called pirate radio, where they don't actually pay a license, so they're breaking the law. But if you're doing it legally, you have to pay a lot of money for a certain bandwidth within this entire spectrum. These are the ones we're interested in. So long wave, because it's a long wavelength, medium wave, then short wave, radio, VHF, very high frequency, UHF, ultra high frequency, that's used for television. Then you've got microwaves, covers this big region here. It's all about gigahertz microwaves. Bluetooth, that little chunk there, 2.4 gigahertz Bluetooth users. Then you've got Wi-Fi is a little chunk there, and microwaves are for satellite television and communications and mobile phones. And okay, so these are some of the bits of this big massive frequency chart. We need to know a little bit about these. Long wave radio is from 150 kilohertz to about 300 kilohertz. Learn these frequencies, do some flashcards, get them learned. How can long wave radio travel very long distances? In fact, how can it get over the horizon? Well, it actually diffracts around the Earth's surface, looking at the first diagram. Yeah, so it can travel very long distances. Shortwave radio, from 3 megahertz to about 30 megahertz, used for long distance communications as well, for ham radio, amateur radio. And here the waves can actually bounce off the ionosphere, and they can get over the horizon as well that way. One interesting thing is as the Earth cools down on a night time and the ionosphere comes down, Yes, you start getting kind of fading. The signal gets weaker and stronger. But I remember shortwave radio when I was on holiday and I wanted to listen to the cricket score. I'd bring my shortwave radio with me and I could listen to the BBC World Service. This is way before the internet was used as much as it is now. Obviously, satellite communication, microwaves can travel through the Earth's atmosphere, and then you can use a satellite to relay signals to a very, very large area, and again to get over the horizon. So microwaves from 2 gigahertz up to 100 gigahertz. Here are some different uses of microwaves: mobile phone networks, satellite systems, Bluetooth. They call them cell phones, yeah, because around the country you've got lots of cells and there are receivers and transmitters within each cell. And when you make a phone call on your mobile phone, that information is traveling from cell to cell to cell to get to where you want it to go. Satellite systems there, again, line of sight. In other words, they won't work if there's stuff in the way. Very large bandwidth, lots and lots and lots of information. Okay, lots of this time division multiplexing going on. Secure, because a lot of encryption is used. Okay, a lot of coding, so that the people who get hold of the signal don't know what it means because it's all coded up. No direct link, but can be very expensive. Obviously, putting satellites into space is very, very expensive. The signal received by the satellite, this is something that you need to know. The satellite receives a signal and then it transmits the signal out, because all the satellite does is relay it, but it receives a very weak signal, that's the uplink, and then it transmits a very strong signal, and that's the downlink. And there is a danger that the signal that it sends out will just swamp the receiving part of the satellite. So what you do is you send it at a different frequency, and so that the receiver and the transmitter are working at different frequencies, and that's to avoid, as I said, desensing, it's called, and that's where you swamp the receiving dish with what's coming out of the sending dish. A little bit about Bluetooth, limited bandwidth. So Bluetooth, you can't really Bluetooth high quality, high definition television, but it's pretty good for music. Short range, again, line of sight. Useful for low power portable devices like a game controller. Look at these questions then. It's discuss how long wave and short wave and microwave links can be used to go above the horizon. Talked about that. Talk about the frequencies, etc. Typical uses, use diagrams, 6 marks. The next one, compare the advantages and disadvantages of optical fibers and copper wires for transmitting information. So, as I said, learn a little bit about how much each one works, be able to compare them, advantages and disadvantages, how secure they are, how much they cost, how easy they are to use. Basically, the information that's in this video.